Hello everyone, welcome to the course on signal system. This is lecture 4 and in this lecture we will see how we can calculate the inverse Laplace transform, and after that we will see the system function and some properties. So as people are already aware that if we have a signal x of t, we can calculate the transform of the signal by utilizing this analysis equation, which is minus infinite to infinite x of t e raised to power minus st dt. So with the help of this particular formula, we can calculate the transform of a signal xt, and we have seen in our first lecture that we can also calculate the inverse Laplace transform with the help of this equation. So while we are computing the inverse with this particular with the help of this particular equation, it basically requires a lot of knowledge of the contour integration, which is basically not easy to solve. So basically we employed a partial fraction expansion technique. We'll be performing the partial fraction of the transform function x of s. After that, we can take the inverse of that particular x of s. So this basically method we are going to utilize to calculate the inverse Laplace transform. Now, the system function and system properties, we are talking about a LTI system. So the LTI system, if we must remember that if ht is the impulse response of the system and xt is the input, yt is the output. So if we recall that a causality, what is causality? So LTI system, first of all, we start with the causal LTI systems, or before LTI systems, we said that if the present output depends on present and past values of input, then the system is said to be causal. If the system is also depending upon the future value of input, that means we can say that the system is non-causal. So with the help of this particular knowledge, we derived a small condition that if h of t is equal to 0 for all t less than 0, if this equation or this condition is satisfied, then we can say that the LTI system is said to be causal. So this is the method in time domain by which we can say that the LTI system is causal or not. So we start with the first condition that LTI system is causal if its impulse response is causal. So a causal function, however, is inherently right-sided. Means we can say that if h of t is 0 for all t less than 0, definitely the h of t is nothing but right-sided. If the signal is right-sided, or if the impulse response of a system is right-sided, definitely the ROC has to be right-sided as per the property of ROC. We have seen that if xt is right-sided, then ROC is right to the rightmost pole but does not contain any pole. So we are going to utilize the same knowledge here, or we can say consequently from the properties of ROC of the Laplace transform, we must aware this. Now the ROC associated with the system function or the transfer function of a causal LTI system is a right side plane or the entire complex plane. We can see for a LTI system with a rational system function h, the causality of the system is equivalent to the ROC of h being the right half plane to the right of the rightmost pole. If h has no poles, the entire complex plane will be the part of ROC. So what we can say that here we want to add one more point, that if impulse response is right-sided, so definitely the ROC is right to the rightmost pole. But it doesn't guarantee that if right to the rightmost pole we have definitely means the reciprocal. Means if we have a right to the rightmost pole ROC, so then the corresponding LTI system is causal also. It is not true, because we can take one example that if we have the impulse response for two cases, one is like this. So let's say if we want to express this signal in terms of an equation, so this is nothing but, let's say, -1, so u of t plus 1, whereas this is h of t equals to, let's say, u of t. So if we can see the transform is nothing but e raised to power st naught multiplied by s of s. So it is e raised to power s divided by s, whereas the transform for ut is nothing but 1 by s. So for both e raised to power s by s and 1 by s, the ROC is real part of s greater than 0. So for both LTI systems, we have the ROC greater than 0, real part of s greater than 0, means the right to the rightmost pole does not guarantee that the LTI system is causal. This is a very, very important point. So after this, for the LTI system, we have the numerical for LTI system with each system function h below determine whether the system is causal or not. So first of all, we have hs equal to 1 by s plus 1. So clearly it is given that real part of s is greater than minus 1. Second is, so we can comment on the type of signal here or the type of system here. So if the ROC is greater than minus 1, if the ROC is right to the rightmost pole, so definitely the HT here is left sided or right sided. We can say that it is right sided because we have real part of s greater than minus 1. For second case, 1 by s square minus 1, we have ROC is both sided. So if we must recall the properties of Laplace, properties of ROC, so if xt is both sided, so the ROC will be between two poles. So this situation is, this problem number B, situation is the ROC which is between two poles, minus 1 and 1. So definitely the impulse response must be both sided. It is nothing but both sided. Next, e raised to power s divided by s plus 1. We have real part of s less than minus 1. So less than minus 1, definitely it signifies that the system is a left sided system. After that, we have h of s e raised to power s divided by s plus 1. Again, we have ROC which is something real part of s greater than minus 1. So definitely it is a right sided system. So if it is both sided, we can see that we can comment directly. If it is both sided, so definitely it is non-causal. Similarly, this is less than minus 1, it is left sided. So again, left sided means definitely it will be non-causal. So this part B and C both are non-causal, and we need to check for part A and D separately. So how we can check? We can basically calculate h of t here. So h of t for first one can be written as h of t equals to, if we can remember, it is nothing but 1 by s, and again there is some shifting. So 1 by s is nothing but u of t, and shifting in s domain 1 by s plus 1. So definitely the property is it is shifting in s domain. So e raised to power minus of s naught is 1, e raised to power minus tut. So e raised to power minus tut, definitely it is a stable, it is a causal. So first one is definitely a causal. Second one we can see, we can directly, if we can remember, it is nothing but something e raised to power minus a mod t. So it is both sided, and if it is definitely both sided, so the impulse response ht is non-causal. It is non-causal. Next, 1 by s plus 1, definitely real part of s, it is given that less than minus 1. We have already written left sided, so definitely it is also non-causal, because if we are going to calculate what is the inverse Laplace transform, so definitely it will be having u of minus t type. U of minus t type, definitely the system is non-causal. Similarly, e raised to power s divided by 1 plus divided by s plus 1, whereas real part of s greater than minus 1. So we can calculate directly what is ht here. So first of all, we have 1 by s. So 1 by s means we have some ut type. After that, we have some e raised to power st naught. So this is nothing but u of t plus 1, and because of this shifting in s domain, we have e raised to power minus s naught t. S naught is basically 1 here. So we have minus t u of t plus 1. So clearly, if we can plot u of t minus 1, we are already aware. So may be definitely of this type. So clearly, we can see that h of t here, it is not 0. H of t is non-zero. If it is not 0, then we can say that for all t less than 0, because we have some h of t left for this particular region. So the system is non-causal here. So we have only one transfer function is given, which is hs equal to 1 by s plus 1 for all real part of s greater than minus 1 is a causal, and the remaining 3 are non-causal. We can see here part A and part D. Both are having the same ROC, but by seeing directly what is the ROC here, we cannot comment that the system is causal or not, because right-sided system does not, the right-sided ROC does not guarantees that the system is right-sided. So only first is causal, otherwise remaining B, C, D or all three are non-causal cases. Now the second property here is the BIBO stability. So before starting with the stability of LTI system, if we must remember that BIBO stands for bounded input, bounded output. Bounded input and bounded output. So if we are saying that if we are providing a bounded input to a LTI system whose impulse response is given by ht, so if the output yt is bounded, then we can say that it is BIBO stable. The system is BIBO stable. And if we can see that if we are providing some bounded type of signal and we are getting a output which is unbounded, so the system has to be unstable type of system. So if we must remember, we have the condition in time domain to check that the LTI system is stable or not. The condition was the impulse response ht must be absolutely integrable. Absolutely integrable means some finite value. So if xt is, if it is absolutely integrable, that means we are having some finite value, and definitely the system is going to be, the system basically converges. If the system converges, so definitely the system is a stable system. So this is the first way in time domain we can see that the system is stable. The second method by which we can say that the transfer function hs is stable is this one. So we must plot the location of poles. If the location of poles is lying in left hand side of S plane, if all the poles of the system function or the transfer function hs lying in the left hand side of S plane, that definitely guarantees that the system is stable. Next we have a causal LTI system with rational system function h is bounded, is BIBO stable if and only if all the poles of hs lies in the left hand side of plane. Means this point I have already mentioned here. Next point, the next point was that if the system is stable, then the ROC must contain j omega axis. The ROC must contain j omega axis. Means we have some cases like this. One case. So definitely we have the ROC, and this particular ROC, the j omega axis is contained. We have the next case like this. So if the ROC is this, definitely we can say that the ROC does not contain the j omega axis and the system is said to be unstable. Here we have the stable kind of a system. So later on we'll see some other cases also which includes some left-sided signals like this. Like this. So although it is left-sided, but again definitely it contains j omega axis and definitely it is going to be stable. And also by seeing this type of ROC, we can comment that the impulse response is left-sided, and if the impulse response is left-sided, definitely it is a non-causal system. So after this, we have some numerical based on the how to check the stability, BIBO stability of the system. So we have the transfer function h of s given 1 by s plus 1 and 1 by s plus 2, and what all possible cases we have if we can draw over here. So we have one pole lying at -2, we have one pole lying at -1. So we have three cases. First case is when real part of S is less than -2, means the ROC is left to the leftmost pole. So definitely the HT we are getting over here is nothing but left-sided. The HT is left-sided. Next case, which is between two poles, which is B part. So when the ROC is both sided, definitely the HT is both sided. And finally, the third case, where we can see that clearly that -1 real part of S is right to the rightmost pole. So definitely HT is right sided. HT is right side. So we can comment also that in all these three cases, in which case the system is stable. So we can clearly see the first ROC over here. So definitely this ROC does not contain j omega axis. So in the first scenario, when we have the real part of S less than -2, the system will be definitely unstable. Second case, when real part of S is between two poles, again we can see that -2 and -1, no j omega axis is contained. So definitely again the system is unstable. Third case, when real part of S is greater than -1, so greater than -1, definitely the ROC contain j omega axis. So once the j omega axis is contained, we can say that the system what we are going to have h of t is right sided, and the system is stable. So we can see that in order for the system to be BIBO stable, the ROC of h of s must include the entire imaginary axis, or the j omega axis must be contained in the ROC. So therefore, we can see that only the third case satisfies, which is real part of S greater than -1. Now we have the LTI system and their differential equations. So we have several type of equations, and we have the differential equations with constant coefficients. So we can basically solve those type of equations with the help of Laplace transform, where m and n, they are the order, mth order. This is with respect to the input here, and this n here we have the nth derivative for the output variable. So we have the transfer function. That transfer function, it's a ratio of Laplace transform of output to the Laplace transform of input, where the input conditions are, where the initial conditions are 0. This is the definition for Laplace transform. So we have some h of s in terms of ys by x of s. So we have one last question based on the differential equation. So consider a continuous time LTI system for which the input and output yt and xt, they are related, which is y double dash t plus y dash t minus 2 times of yt equal to xt. So first of all, first point is find the system function or the transfer function. So how can we calculate the transfer function? First, we are going to apply the Laplace transform to this entire equation. So it would be, this is s square ys plus s times of ys minus 2 times of ys equals to x of s. So by taking common ys over from the left hand side, I can have ys by x of s equals to h of s, which is nothing but 1 by s square plus s minus 2. S square, 1 by s square plus s minus 2. So with the help of this, we have the first part, the system function or the transfer function. Next is determine the impulse response ht for each of the following three cases. What all cases we have? First is the system is causal. Second is the system is stable. Third is the system is neither causal nor stable. So how can we start with this? So we can start by plotting the location of poles. So the poles can be calculated or the plotted. First of all, we have the partial fraction for this. So it is s plus 2 s minus 1. So definitely the location of poles is plus 1 and next is minus 2. So we have two poles, one is at plus 1, one is at minus 2. So first of all, we can have the answer for the second case, the system is stable. So we have three possible ROCs. First possible ROC is, which is to the left, real part of s less than minus 2. Here we have real part of s greater than 1, and we have real part of s which is between minus 2 and plus 1. So only in this particular scenario where we have real part of s greater than minus 2 but less than minus 1, the system is stable. Otherwise, the system is not stable. And the third case, the system is neither causal nor stable, means definitely it must not contain the j omega axis, and it has to be the non-causal. So definitely the system has to be left sided. So the answer for this is real part of s less than minus 2, and the answer for first part is when real part of s greater than plus 1. So for all these three possible cases, we need to calculate what is h of t. So first of all, how can we start? We start with the inverse Laplace transform. So inverse Laplace transform will be having the h of s first. Next, we'll take the partial fraction. So the partial fraction will be 1 by minus 1 by 3, this particular factor and this particular factor. So first of all, when it is causal means the signal has to be right-sided, real part of s greater than 1. So means the inverse of both this one and this one has to be right-sided. So this is our first question, e raised to power minus at u of t, the transform was 1 by s plus a. If we can compare both, so we can see that 1 by s plus 2, so it is both we have ut factor like this. So this is causal. And the remaining two part, which is stable and unstable, stable and neither causal nor stable, we have already seen what all possible ROCs we have. So these are the references. Thank you.